On behalf of Kamnoetvidya Science Academy School, I'm proud to present our research, Effect of Magnetic Field on the Frequency Generated from an Active Magnetic Buzzer. My name is Settasit Settagaroon, with teacher Kriangamon Sawangsri as our advisor. My presentation divided into 5 parts as shown. I will start with some general information on a magnetic buzzer. It is one of the most widely used electronic devices to generate the beep sound frequency. In general, magnetic buzzers are divided into 2 types, which are passive and active. The active magnetic buzzer additionally contains 555 timer IC as an oscillator circuit that encourages it to work with DC. Here is where something interesting happens. I'm showing that when we point a magnet bar to the buzzer, the frequency is decreased, and when we point another end of the magnet bar to the buzzer, the frequency is increased. Here I have an active magnetic buzzer connected with Arduino Nano, which works as an electrical supply. Next, I will turn it on and point one side of a magnet to it. Then, I will switch the side of the magnet. Let's hear what it sounds like. With suspicion on this phenomenon, we institute our research with the objectives: first, to explain the change in frequency generated by an active magnetic buzzer to the applied external magnetic field, and second, to construct a mathematical model describing the relationship of the generated frequency as a function of magnetic field strength. Now, we are moving to the theoretical derivation. We know from the datasheet of 555 timer IC that the frequency of the pulse generated is dependent on the capacitance of the capacitor in the circuit. The capacitance is calculated from the well-known formula number 1. For external magnetic field intensity H, the magnetic force acting on the capacitor that occurs due to dipolar interactions between plates can be calculated from equation number 2, acquired from previous research on the magnetorheological elastomer. We assume that the magnetic force is an elastic force acting on the magnetorheological elastomer. Therefore, we can write it in the form of Hooke's law in equation number 3. From now on, we can transform the equation into the form that shows the final distance between plates in equation number 4 and form that shows the final capacitance of the capacitors in equation number 5. Finally, we substitute the capacitance in the equation from the datasheet to get the final model in the red box, which variable h squared is the vector quantity. It will be positive when the vector points toward the buzzer, and will be negative when the vector points outward from the buzzer. Our constant could be acquired from the experiments and previous researches. To confirm the model, we experimented by setting up three-way Helmholtz coils provides the external magnetic field. Then the TOGOT 5-volt electromagnetic active buzzer is placed on the feature board in the center of Helmholtz coils in the direction that the magnetic field points toward and outward from it. After that, we adjust magnetic field strength with a scale of 0.5 millitesla at a time, from 0 to 3 millitesla. Results display the magnetic field strength on x-axis and the frequency generated on y-axis. Here we show the comparison between the theoretical line and experimental regression line. In this graph, the magnetic field points toward the active magnetic buzzer. The result shows that the frequency generated is directly proportional to minus h squared. Furthermore, the result agrees with the mathematical model with an r-squared value equal to 0.96. This is another case, which the magnetic field points outward from the active magnetic buzzer. This graph seems to be linear, since the three-way Helmholtz coil has a limitation that can produce the maximum magnetic field intensity at only 3.2 millitesla. For that reason, we could not experiment with higher magnetic field intensity. Therefore, we expect to see a quadratic graph of the result with stronger magnetic field intensity and more experimental data. Another assumption on the variance between the theoretical line and the experimental reflection line on both graphs is a magnetic field measuring problem. All measuring instruments have dimensions, as you can see from the illustration. The closest position we can measure the magnetic field is around a centimeter from the center of the buzzer. Even fewer Helmholtz coils generates a stable magnetic field in the center, but a high possibility of having an unwanted magnetic field generated inside the circuit part is hard to deny. To improve the model, we have to figure the way to detect this unwanted magnetic field and add it to be another constant in our equation. To conclude, the sound frequency generated is indicated by the pulse frequency acquired from 555 timer IC. The applied external magnetic field creates stress in magnetoroological or MR elastomer located between flat plates capacitor and thicken or thinner the distance between the plates, which respectively change the capacitance of the capacitor. The change of capacitance will affect the pulse frequency. Finally, the result is shown in the change of sound frequency generated. For further research, we plan to institute research on finding the dependence of this phenomenon due to the different types of MR elastomer materials to make this research application in designing an active magnetic buzzer or even magnetic field sensors. Thanks you all for listening.